Hello everyone, welcome to my YouTube channel. I am Kiran. So today I am going to explain you guys about scalability and data-driven parallelism in sparse matrices in a clear-cut manner, and I am going to discuss about the key points and challenges involved in it. Let us move on to the topic. So firstly, what are sparse matrices? A sparse matrix is a matrix in which most of its elements are zeros. As you can see in the given figure of sparse matrix, only a few of its elements are non-zeros, whereas on the other hand, a dense matrix is a matrix in which most of its elements are non-zeros and a few are zero elements. Sparse matrices are commonly found in scientific computing and machine learning. Efficient storage and computation techniques are crucial for handling sparse matrices because they contain so many zeros. Storing and processing these matrices directly as if they were dense would be inefficient in both memory and computational resources. Scalability and data-driven parallelism are critical concepts in computer science and software engineering, especially when dealing with high-performance computing, big data processing, or distributed systems. Let's dive deep into these concepts using easy-to-understand analogies and then explore the technical details. Scalability is nothing but growing efficiently. To understand this, let us go on with an analogy. Imagine you are running a small cafe. Initially, you can handle everything on your own, taking orders, making coffee, and serving customers. As more customers start coming in, your cafe becomes busier and you find yourself overwhelmed. To handle this growth, you decide to hire more staff, a barista to make coffee, a cashier to take orders, and a server to deliver drinks. Now, your cafe can handle more customers without you doing all the work alone. Scalability in computing is similar. It's about a system's ability to handle increased load by adding more resources, like more servers, CPUs, or memory, without significantly degrading performance. It is essential for applications that deal with large datasets and complex computations. So, what are the types of scalability? There are two types of scalability. The first one is vertical scaling. We also call it as scaling up. In this, we add more power to your existing machine, like upgrading to a faster CPU or adding more RAM. Think of it like upgrading your cafe's equipment to make coffee faster. And the second one is horizontal scaling. We also call it as scaling out. In this, we add more machines to handle the load. This is like hiring more staff in your cafe. Each new worker helps handle more customers. Why scalability matters? Scalability is essential because it ensures that your application can handle increased demand smoothly. For example, if an e-commerce website can't scale properly, it will slow down or crash when too many people try to buy during a sale. Scalability in sparse matrices. There are two cases involved in it. The first one is memory efficiency. Since sparse matrices only store non-zero elements, allowing algorithms to scale to larger datasets without running out of memory. And the second one is computational efficiency. They perform fewer operations as there are only few non-zero elements in a sparse matrix. This is crucial as the size of the matrix grows, allowing the algorithm to process larger matrices without a proportional increase in computation. Data-driven parallelism. In this, we divide the given work and we will conquer what we want. Let us see the analogy of it. Imagine you are tasked with assembling 1,000 toy cars for a toy store. Doing it alone would take you much more time. But if you have a team of 10 people, you can divide the work so that each person assembles 100 cars. Better yet, you split the assembly into stages. One person handles the wheels, another the body, and so on. This way, the work is done simultaneously and the cars are assembled much faster. Data driven parallelism works on the same principle. It's about breaking down a large dataset or computational task into smaller pieces and processing them simultaneously across multiple processors or machines. How data-driven parallelism works? It works based on four steps, and the first step is divide. In this, the data or tasks are divided into smaller chunks. In the second step, which is distribute, the chunks are sent to different processors or nodes for execution purpose. And in the third step, which is conquer, each processor works on its chunk independently. And in the fourth step, which is combine, the results are aggregated to form the final output. For example, imagine sorting a massive list of numbers. First, split the list into smaller sublists. Then, each processor sorts its assigned sublist. Then, all sublists are merged into one sorted list. So, what are the key concepts in data driven parallelism? The first one is data partitioning, dividing data into independent chunks. We divide the given data into independent chunks here. Think of slicing a pie, each slice can be eaten separately. The second one is task scheduling. Here we decide which processor gets which chunk of data. It's like assigning each worker their part of the assembly process. And the third one is load balancing. In this, we ensure each processor get a fair share of work, so no one is idle, similar to making sure no worker has too many tasks while others have too few. So, the technical details and challenges of it. The first one is synchronization. We ensure that all processors work well together. The case is that if all the processors will not work in the same speed, we commence up with a problem known as bottleneck problem. Imagine if some case workers are too fast and others are too slow. This creates the problem. And the second one is communication overhead. The cost of coordinating between processors. It's like the time your staff spends talking to each other instead of serving customers. And the third one is scalability limits. Sometimes adding more processors doesn't help and can even slow down things due to increased overhead. It's like too many people in a kitchen where they start getting in each other's way. And the fourth one is fault tolerance, handling failures gracefully. If one worker makes a mistake, the cafe shouldn't come to a halt. Similarly, if one processor fails, the system should continue functioning. Data-driven parallelism in sparse matrix. Parallel processing of non-zero elements. In a sparse matrix, only the non-zero elements need to be processed. Data-driven parallelism allows different processors to handle different non-zero elements independently, as long as there are no dependencies between them. And the second one is asynchronous execution. Data-driven parallelism often allows processors to work asynchronously. This means that each processor works on a piece of the matrix without waiting for others, which is particularly helpful in sparse matrices where the non-zero elements are spread out unevenly. And the third one is dependency management. In operations like matrix multiplication, processors must account for dependencies where certain calculations rely on the result of other calculations. Data-driven parallelism helps manage these dependencies dynamically, allowing the processors to perform computations as soon as required data is available, without waiting for an entire row or column to be processed. So, what are the applications of data-driven parallelism? The first one is big data processing. In tools like Hadoop and Spark, we use parallelism to process massive data sets efficiently. In scientific computing, simulations and models like weather forecasting often rely on breaking tasks into parallelizable chunks. And machine learning, training models on large data sets is sped up significantly using data driven parallelism. And I hope you understand about scalability and data driven parallelism clearly. Thank you.